Hello, this is video section 7.3, logarithms and logarithm functions. All right, so let's not get scared. So our vocabulary, we have two vocabulary words, logarithms, logarithm functions. They're pretty self-explanatory, but we're going to go over them in just a minute. And our objectives are to evaluate a logarithm expression and to graph a logarithm expression. So let's get right into 7.3. So the first thing is, let's go back and let's just recall our exponential function that we just got through doing. So f of x equals 2 to the x. And we're going to look at the function 2 to the x and its inverse. So remember, we can make a table for x and then find y by putting it into the function. And then its inverse, remember, we just switched the y and x's, and what else is switched? The x and y coordinates. So we don't even have to evaluate, we just know because it's the inverse, we just swap the coordinates. We can graph them and you can see they reflect over the line y equals x. So this is y to the 2x and this is x equals 2 to the y. As the value of y decreases, the value of x approaches 0. All right? So the inverse of y equals 2 to the x can be defined as x equal to the y. So in general, the inverse of y equals b to the x is x equal b to the y. And this is important because when we have x equal b to the y, okay, y is called the logarithm. Y is called the logarithm of x. Okay, so that's what logarithm is the inverse, it's y of the inverse of the exponential function. Okay, so this is important to know. It's usually written as y equals log, it's usually written like this, y equals log, and this is read y equals log of base b, log base b of x. Okay, the book doesn't tell you, but x is called the argument. Okay, I like to write this as log. And this is going to be, it's not important now to know the x is the argument, but it will be important later on when we're solving and doing stuff. So go ahead and learn it now and understand that that is the argument. The whole thing, x, is called the argument. Okay, so all I did was use the symmetric property and change these two to get this form here. Okay, so let's look at the key concept box of what a logarithm with the base b. Now you see it's written down at the bottom as a subscript, which we can kind of say is a base because at the bottom we think of base normally as the bottom. So if we let b and x be positive numbers, okay, b, the argument x and the base b, and b cannot equal 1, then the logarithm of x with base b is denoted log base bx and is defined as the exponent y that makes the equation b to the y equals x true. So it's a bunch of fancy words. So basically they're saying if b and x are greater than 0, they're positive, and b is not 1, then there is a number y such that if we take the log base b of x equal y, this is true if and only if b to the y equals x. Okay, so the way they write it is a little confusing. I'm going to show you a better way so you're not having to memorize what goes where. So let's look at the example. So they say, so basically if you write the log over here, so remember it is a base. B is a base. Okay, so what do we know about exponents? I'm going to write b to the y. B is my base and y is my exponent. So if you write it this way, to write this into exponential form, you keep your argument's going to equal to b is the base of the log, it's also the base of the exponent. So you have x equal b to the y. Okay, so it makes it less confusing. So let's look at the example, which says if we have log of base 3 of 27. Remember, that's my argument. So identify the pieces and equal y. To write this in exponential function, we just simply take this and move it up, and we drop the log. So we say the argument is equal to the base 3 raised to the y power. Okay, so of course they're going to write it. Remember, you have a symmetrical property, so these equal the same thing, but this makes it much easier. You're not memorizing, you're not having, it's one less thing you have to memorize. You just know it's a base, and when you change it to exponential function, it's still the base. It just raises the y, or the logarithm, into the exponent. Okay, so let's look at some examples. Let's look at example 1. So they want us to, so by definition, we can change from a logarithm to an exponential, and an exponential back to a logarithm. So let's look at the examples that they give us. Example 1. So they want us to write log base 2 of 8 equals 3 into an exponential function. So first of all, I'm going to identify what's my base. My base is 2. My argument is 8. So this just goes up, and I say 8 equals 2 cubed. Is that a true statement? Yes, it is. What about this one? Log base 4 of 1 over 256 equal negative 4. So again, identify your pieces. This is my argument. This is my base. So then how would I rewrite this? Well, then I would take, find some colors here. So then I would take this and move this up, and I would say 1 over 256 equal 4 to the negative 4 power. You put 4 to the negative 4 power in your calculator, you'll get 1 over 256. Okay? Likewise, let's look at example 2. We can write an equation in logarithm form from exponential. Again, if you keep your log over here on the left side, and when it's an exponential form, you keep your exponent to the right, and you keep your argument to the left, then it makes it really easy. You're not memorizing. So let's look at the example 3. They want you to write 15 cubed equals 3375 into logarithm form. So the first thing I'm going to do is I'm going to switch the place. Because then I know in order to write this into logarithm, I add my logarithm here, my base comes over here, so I have log base 15 of 3375, which is my argument, equals 3. Makes it much easier when you do that. You just know it goes down. Let's look at the next example. They want us to write 4 to the 1/2 equals 2. Again, I'm going to switch the places. 2 equal 4. Remember, this is my exponent. So, in order to do this one, I'm going to add the log over here because my exponent's on the right, and my base is going to move down here. So then I have log base b of 2 equal 1/2. Okay, so it's easy to go from exponents to logarithm and then logarithm to exponential form. So we see that an exponential function is an inverse of a logarithm function. All right, so now, saying that, let's look at the graphs of logarithms. Okay, so we've done these examples. So graphing logarithms. So what is a logarithm function? Is your vocabulary, your second vocabulary. It's basically a function with a logarithm in it. So the function y equals log base b of x, where b cannot equal 1, is called the logarithm function. So x represents a parent graph of the logarithm function. So just like everything else, we have a parent function. So we have a log base b of x equals f of x. Remember, f of x is a fancy word for y. Alrighty, and we saw that earlier. And when we're solving and evaluating, we're going to flip them the other way, okay? But for right now, this is how we have it. So this is our parent function. Again, the parent function is the argument x with logarithms. So anything inside of here of the argument, that's why it's important to identify the argument, is inside the function. Just like everything else, we have transformations. So let's look at the key concepts. So let's look at just the basic parent function. So f of x equals log base b of x is your parent function. All right? Do you see it kind of mimics exponential where it's got two. Exponential, we had growth and decay. So we have similar things going on here. So the domain for both of these, doesn't matter, the parent function, is all real numbers. It has an asymptote, but instead of the asymptote being the x-axis, it's the y-axis, which the book refers to as f of x, or we can say x equals 0, because that's the graph, the line of the y-axis. It's continuous, and it's a 1-to-1. You see it passes a horizontal line test, which means its inverse is also a function. Domain means x greater than 0 because we have an asymptote. It doesn't go past, it approaches 0, but never touches 0 or goes past it. Range is all real numbers, and again, the intercept is 1, 0. And notice the 3 coordinates. It still uses the 3 coordinates of 1, 0, 1 over b, negative 1, and b, 1. The difference between these two, it still uses 1 over b and b, and negative 1 and 1, and 1, 0. The difference is between the logarithm and the exponential is the xy's are reversed. But it's the same coordinates. Now, again, you have two things. So remember, when b, the base, is greater than 1, this is what our function, y, f of x, increases as x increases. And when b is between 0 and 1, when it's a proper fraction, f of x decreases as x increases. Okay? So let's look at a graph, an example of graphing. So they want us to graph the function f of x equal log 5x. So first of all, we're going to identify what the base, our base is 5. We're going to use these 2 points, these 3 points, 1 over b, negative 1, 1, 0, and b, 1. Because b is greater than 1, we know it's going to be increasing. So that's why the graph is going to do this. But we can just plug them in the points. So we're going to we replace it. So we have 1/5, negative 1, 1, 0, and 5, 1. We can plot those, and our graph is easy to graph. And we know we have still the asymptote here. Let's look at this next one. Since it's 1/3, we know it's going to be decreasing graph. And again, we just plug these back into the same formula, 1 over b, negative 1, b, 1, and 1, 0. And then we can sketch the graph. All right? So that's easy for a parent function, right? We said, so just like in exponential, our parent functions can change based on what b is. Just like we had 2 to the x, 3x, 1/3 x, it could be log base 2 of x, log base 3 of x, log base 1/3 of x. So it just depends on, they're all still parent functions. Now, we can transform them just like we do any other function, whether it's a quadratic, cubic, absolute value, square root, exponential, now logarithms. That's why it's important to learn this key concept box. So f of x equal a log base b of x minus h plus k. Again, I'm going to add another value that you need to know. So we said f of x equals a log base b of c times x minus h plus k. All right, so I'm adding basically c. So remember, c is equivalent to a, but horizontally. So a has 2 jobs. So what does a tell us? A tells us, did we have a reflection? So if a is negative, we have a reflection over the x, a vertical reflection over the x-axis. And if the absolute value is greater than 1, then we have a vertical stretch. If the absolute value of A is less than or between 0 and 1, then we have a vertical compression. C does the same thing, except for it tells us horizontal. And again, remember we have to do 1 over C. So if C is negative, C has a horizontal reflection, which it reflects over the y-axis. If 1 over C, you have to do 1 over C, and if the absolute value of that is greater than 1, then it has a horizontal stretch. And if 1 over absolute value of 1 over C is between 0 and 1, then it has a horizontal compression of 1 over C. All right. H tells us, did it go right or left? Yes. So we take the opposite, and if it's positive, it moves to the right. If it's negative, it moves. If H is negative, it moves to the left. K, we take it as is, which tells us our vertical translation, up or down. Okay, so this key concept box is exactly like the other ones. The only difference is our parent function is log base b, x minus h. And so remember that this argument must be in factored form if you have a c. It cannot be in distributive form. It cannot be c times x minus c times h. If it's in that form, you must factor it out, the c, to put it in factored form. Okay? Otherwise, you'll get your transformations wrong. So let's look at the example 5. They want us to graph f of x equal 3 log base 10 of x plus 1. So first of all, let's break this down. Okay? So let's break up the equation and identify the pieces. If you identify the pieces, it's not going to be as intimidating. Okay, so what is our argument? It's right here. That's our function. What is 3? And what is 1? Okay, so we can say h is 0 because I don't have x minus anything. C is 1. A is 3. And k is 1. So that tells me if I take my function, it's going to shift to the what? It's going to shift up 1 unit. So 1, remember it's 1 comma 0 is our function. So this is going to shift up 1. It's going to have a vertical stretch, which means it's going to get fatter. But it didn't shift to the right or left, so I still have my asymptote of y equals 0. So we have a vertical stretch, no horizontal shift, and it transfers up. Let's look at b. F of x equal 1/2 log base 1/4 of x minus 3. So our argument is x minus 3, which is our function, x minus h. So we know the absolute value of a is 1/2. Which tells us it's vertically compressed by 1/2. H is 3, it's opposite, and K is 0. So there's no vertical shift. It just shifts to the right. And now we can graph that, and our asymptote now becomes what? 3 instead of 0. Positive 3, so it approaches 3. So remember, the vertical asymptote follows the h now, whereas in exponential, the horizontal asymptote followed k. Okay, and so we do it the same way. It's really easy. You just got to. The key is knowing the parent function of your logarithm, and know that when b is greater than 1, it increases. When it's a fraction, it decreases. And you know these 3 points. This is going to be really important. That's all you really need to graph and give me the 3 points. All right, do the practice problems, and we will see you in class.